The topic for this week's discussion quiz is L'Hopital's rule. This is a theorem that we can use to solve limits. If we look at 1a, what is the limit as x approaches 1 of the natural log of x divided by x squared minus 1? This is an indeterminate form if you try to put 1 in place of x into this expression. You have the natural log of 1 divided by 1 squared minus 1. This is equal to 0 over 0. Because this is an indeterminate form, we can take the derivative of the top and bottom separately and consider that new limit instead. So this should be equal to the limit as x approaches 1 of, if we differentiate the numerator, that's 1 over x, and if we differentiate the denominator, that is 2x. I'm going to simplify this. I'm going to write this as a single fraction by multiplying this denominator and this denominator together, so this multiplies here. We'll have 1 over 2x squared. I won't need this divided by 1 anymore, but I'll write the limit like this. This is the limit as x approaches 1 of 1 over 2x squared. If this limit exists, by L'Hopital's rule, it'll be equal to this limit here. By direct substitution, we can put 1 in place of x, and the limit is equal to a half. And that is the answer to this limit here. Let's try to solve this limit in part B. This one is not written as a fraction, but it is still an indeterminate form. As x goes to infinity, this 5 over x goes to 0, so the whole thing inside the parentheses approaches 1, and the exponent as x goes to infinity as well. This is a 1 to the infinity indeterminate form. The goal is to introduce a logarithm, so we can write this as a fraction in order to apply L'Hopital's rule. So the way I like to do this is, I'm going to say that whatever this limit is equal to, if it exists, it's going to be L. So L just stands for the limit. So if this limit is equal to L, you can apply the natural log to both sides to say that the limit as x goes to infinity of the natural log of 1 plus 5 over x to the power of x is equal to the natural log of whatever this limit is supposed to be. Essentially, going from this step to this step is I took the natural log of both sides. On the next slide, what I'll do is compute this limit. It'll be equal to the natural log of L, and then I can use that information to figure out what L should be equal to. So starting here, using properties of exponents, I can take this x and bring it down front. So this is just a property for logarithms. This is the limit as x goes to infinity of x times the natural log of 1 plus 5 over x. If you want to use L'Hopital's rule, you have to have a fraction. So I know it has to be divided by something, and currently our denominator is equal to 1. We can take this x and place it into the denominator if we write it as 1 over x. So that is, this is the limit as x goes to infinity of, so the top is just going to be the natural log of 1 plus 5 over x, and in the denominator, I'll put 1 over x. So the reason that this step is equal to this one is because if you're dividing by a fraction, you multiply by the reciprocal, which means you would multiply by x. That would reverse this step to this one. So currently, this is now expressed as a fraction. Is this fraction an indeterminate form? Well, as x goes to infinity, this approaches the natural log of 1, and it's divided by 1 over x goes to 0. Since the natural log of 1 is 0, this is really 0 over 0. That's an indeterminate form. We can apply L'Hopital's rule on this fraction. Before I do that, I like to rewrite the expression so it's better for using rules of derivatives. I'm going to write this as the natural log of 1 plus 5x to the negative 1. Likewise, in the denominator, instead of 1 over x, I'm going to call this x to the negative 1. My next step is I'm going to differentiate the top and bottom separately. So here we're applying L'Hopital's rule. The derivative of the top is 1 over 1 plus 5x to the negative 1. So that's the derivative of a natural log. It's 1 over this thing. But by the chain rule, you have to multiply by the derivative of the inside, which is negative 5x to the negative 2. Now, if I differentiate the denominator, it's going to be negative x to the negative 2. I'm going to note here that this is the step where we applied L'Hopital's rule. Okay, before we actually figure out this limit, I think it makes sense to try to simplify as much stuff as possible. For example, this negative and this negative can cancel, so I know this cancels with that. But actually, so does the x to the negative 2 and this x to the negative 2. Those cancel. All that's left over is this 5. It's divided by this denominator, which is now 1. For this reason, I'm not going to write this fraction or the 1 that's left over in the denominator. I'm just going to write this part here, multiplied by 5, and I'm going to put that 5 into the numerator of this fraction. So this is equal to the limit as x approaches infinity of 5 over 1 plus 5x to the negative 1. And then I'm going to go ahead and take this x to the negative 1 and rewrite it as a fraction like this. So this is the limit as x goes to infinity of 5 divided by 1 plus 5 over x. Now, as x goes to infinity, this goes to 0. So this limit becomes 5 divided by 1 plus 0, and this is simply 5. What does this all mean? Well, this is equal to the natural log of the limit of the thing that we started with. So I'm going to open that up on a new slide. So from our previous work, we saw that the natural log of the limit is equal to the natural log as x goes to infinity of this thing. And we just did a bunch of work to show that this whole thing here is equal to 5. So said another way, the natural log of the limit L is equal to 5. You want to solve for L, so I'm going to exponentiate both sides like this. E to the natural log, those are inverses and they cancel. It leaves us with just L, our limit, and our limit is equal to e to the power of 5. This is the final answer for part B.